In April 1995, astronomers pointed the Hubble Space Telescope at a small, unremarkable patch of sky in the constellation Ursa Major. Not at a known galaxy, not at a nebula, not at any object that had been catalogued as interesting. They pointed it at a region of sky that appeared, to conventional telescopes, to be essentially empty. They left it open for 10 consecutive days, collecting light from across that dark void. And what emerged from the accumulated data was an image that changed astronomy permanently. The Hubble Deep Field showed approximately 3,000 galaxies in a patch of sky, and so small that you could cover it with a grain of sand held at arm's length. Not 3,000 stars. 3,000 galaxies, each containing billions of stars, each separated from us by billions of light years. But some of them existed when the universe was less than 1 billion years old. The image made tangible, for the first time in the history of human perception, the scale of what exists beyond the reach of any unaided eye. And it told astronomers something that the subsequent 3 decades of observation have been systematically confirming, and more recently, systematically calling into question. It told them what the early universe looked like. Small, faint, sparse galaxies at the frontier of the observable cosmos. Young galaxies in the process of assembling their first generations of stars. The universe in its infancy, seen across the greatest distances any optical instrument had ever probed. That picture was consistent. It was coherent. It matched the theoretical model, the lambda cold dark matter model, the standard cosmological framework describing a universe 13.8 billion years old, inflated from a singularity, dominated by dark matter and dark energy, assembling its first structures from density fluctuations in the primordial plasma. The Hubble observations fit the model. The model explained the observations. And then the James Webb Space Telescope launched in December 2021 and looked at the same edge of the universe with instruments 20 times more sensitive and capable of seeing wavelengths of light that Hubble could not detect. What it found does not fit the model, not in minor ways, not in ways that require small adjustments to the parameters, in ways that have prompted leading cosmologists to use phrases like completely unanticipated, growing chasm between theory and observation. Yeah, and we really shouldn't have found a galaxy like this given our understanding of the way the universe has evolved. That last phrase was spoken by Kevin Hainline of the University of Arizona. He was describing a specific galaxy, JADES-GS-Z13-1, which the JWST found existing only 330 million years after the Big Bang. What made it not merely distant, but impossible, in the strict theoretical sense, was the specific light it was emitting. The galaxy was producing Lyman alpha radiation, high-energy ultraviolet light emitted by hydrogen gas that has been ionized by energetic photons from young stars. This radiation should not have been detectable from this galaxy at this era. At 330 million years after the Big Bang, the universe was still largely filled with neutral hydrogen, the primordial fog that preceded the era of reionization. Yeah, this fog absorbs Lyman alpha radiation completely. A galaxy trying to send Lyman alpha radiation through this fog should have had its signal extinguished before it traveled any significant distance. The signal was not extinguished. It came through, clear, detectable, anomalously strong. Something had cleared a path through the primordial fog that should not have existed yet. Something had ionized the neutral hydrogen around this galaxy before the universe had developed enough energetic sources to do this on the scale required. The observation was described in the journal Nature. The research team stated, with the specific restraint that scientists use when they don't know how to explain what they've found, whatever the galaxy is concealing, it is certain to illuminate a new frontier in cosmology. Now, that is the language of discovery colliding with confusion. It is the language of data that the models cannot accommodate. This is one of several such collisions, and together they are building a picture of the very beginning of time that does not match what 30 years of cosmological observation and theoretical refinement predicted. To understand why this is so disturbing, you need to understand what the standard model of cosmological structure formation actually predicts. The lambda CDM model, lambda for the cosmological constant describing dark energy, CDM for cold dark matter, describes the formation of galaxies as a hierarchical process. It begins with tiny density fluctuations in the primordial plasma of the early universe, but quantum mechanical variations that were present in the first fractions of a second after the Big Bang, and that were amplified by the period of inflationary expansion that immediately followed. These fluctuations are observable today in the cosmic microwave background, the faint afterglow of the Big Bang, measured with extraordinary precision by the COBE, WMAP, and Planck satellite missions. The specific pattern of the CMB fluctuations is the seed pattern from which all cosmic structure grew. Dark matter halos, vast invisible concentrations of dark matter, collapsed first under gravity in Italy, providing the scaffolding into which ordinary matter fell to form the first stars and galaxies. The halos grow hierarchically. Small halos collapse first, then merge into larger ones, which merge into still larger ones. Galaxies form inside the halos. Yet the mass of a galaxy is limited by the mass of the halo that forms it, and halo masses grow with cosmic time. The natural consequence is that the earliest galaxies, those forming within the first 100 million to billion years, should be small because the halos available at that epoch are small. They should be faint because they have not yet had time to form many stars. They should be few in number because galaxy formation is just beginning. When the JWST was designed, the theoretical models predicted that at redshifts above 10, corresponding to a time when the universe was less than 480 million years old, galaxies would be so small and faint that detecting more than a handful of them would require the deepest possible observations. The instruments were calibrated with this expectation. But the reality was different by a factor of approximately 100, not 10, not a factor of 2 or 3 that might be explained by adjusting star formation efficiency parameters, a factor of 100. The JWST has found approximately 100 times more bright galaxies in the early universe than the lambda CDM model predicted. Not dim galaxies at the edge of detection, bright galaxies, sometimes luminous enough that the team calculated they could have detected them even if they were 10 times fainter. Galaxies so bright, so large, and so chemically mature that their existence at such early times strains the model's ability to accommodate them even with generous adjustments to the astrophysical parameters. The galaxy designated MOM-14, the most of most, the HUS, named for its record-breaking properties, was confirmed in April 2025 and published in the Open Journal of Astrophysics in February 2026. It exists at redshift 14.44, corresponding to a time only 280 million years after the Big Bang. It is, as of its publication, the most distant spectroscopically confirmed galaxy ever found. And it is, according to NASA's own description, brighter, more compact, and more chemically enriched than astronomers anticipated for such an early era. The chemical enrichment is the most disturbing detail. At 280 million years after the Big Bang, a galaxy should contain almost no elements heavier than hydrogen and helium. The first stars, called population 3 stars, the hypothetical first generation, formed from pristine primordial gas containing essentially only hydrogen, helium, and traces of lithium. These stars produced the first heavier elements through nuclear fusion and dispersed them into the surrounding medium when they exploded as supernovae. The second generation of stars, forming from the enriched gas, would then incorporate those elements. This process takes time, multiple stellar generations, each with lifetimes of millions to hundreds of millions of years. MOM-Z14 shows elevated levels of nitrogen. Nitrogen is produced in specific types of stars, including intermediate mass stars with relatively long lifetimes. Its presence in a galaxy at 280 million years after the Big Bang requires explaining how multiple generations of stellar evolution could have occurred in less time than the standard models allow. The team itself noted that the galaxy appears to have cleared its surrounding region of primordial hydrogen gas, an unexpected finding, given that early universe ionization was supposed to be a much more gradual, prolonged process. Jacob Shen, a postdoctoral researcher at MIT on the team that discovered MOM-Z14, stated it with rare directness. There is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. A growing chasm, not a discrepancy, not an anomaly, a chasm. Now consider what Hubble specifically contributed to establishing the picture that JWST is now challenging, because the contrast is important. The Hubble Space Telescope, launched in April 1990 and still operational in 2026, has been the foundational instrument of modern observational cosmology. Its primary mirror, 2.4 meters in diameter, operates primarily in ultraviolet visible and near-infrared wavelengths. In 1995, the original Hubble Deep Field observation revealed approximately 3,000 galaxies in a tiny sky patch. In 2004, the Hubble Ultra Deep Field extended this to approximately 10,000 galaxies. In 2012, the Hubble Extreme Deep Field, produced by combining 10 years of ultra deep field observations, revealed approximately 5,500 galaxies in an even smaller field. These images represented humanity's deepest look at the universe, pushing the observable frontier to galaxies at redshifts up to approximately 11. Objects existing approximately 400 million years after the Big Bang. At redshift 11, Hubble found GN-Z11, at the time the most distant confirmed galaxy, a remarkably bright object that itself defied expectations. Scientists noted that GN-Z11 was unusually luminous for its epoch, but it was a single data point, an anomaly that could be attributed to a particularly favorable combination of conditions. JWST confirmed GN-Z11's distance and then moved past it, finding not one anomalously bright galaxy but hundreds. The phenomenon is not a fluke. The reason JWST can see what Hubble cannot is wavelength. The expansion of the universe stretches the light from distant objects toward longer wavelengths. A galaxy at redshift 14, existing only 280 million years after the Big Bang, has had its light stretched by a factor of 15, moving even the ultraviolet emission of its young stars into the mid-infrared wavelengths that only JWST can detect. Hubble is essentially blind to objects beyond redshift 9. Everything that JWST is finding at redshifts above 10 was invisible to Hubble, present in the sky for decades but undetectable. The universe's infancy was hidden not because it was too far away in a physical sense, but because it was emitting in wavelengths our most powerful tool could not register. What JWST is now seeing in those wavelengths is a universe that assembled itself faster than physics says it should have. The galaxy Virgil, described in a December 2025 paper as a cosmic Jekyll and Hyde, exemplifies the hidden complexity that JWST has revealed in apparently ordinary objects, seen through JWST's near-infrared instruments. Virgil appeared to be a typical young star-forming galaxy at approximately 800 million years after the Big Bang. Routine, unremarkable, another data point in the survey of early galaxies. When observed with MIRI, JWST's mid-infrared instrument, Virgil transformed into something entirely different. The host of a heavily obscured supermassive black hole pouring out immense quantities of energy, previously completely hidden by dust. The black hole at Virgil's center is accreting material at a rate far exceeding what current models predict for its host galaxy's mass. George Ricci, the Regents Professor of Astronomy at the University of Arizona who leads the MIRI science team, described what this discovery means for the standard picture. JWST has shown that our ideas about how supermassive black holes formed were pretty much completely wrong. Well, it looks like the black holes actually get ahead of the galaxies in a lot of cases. Get ahead. The standard model of galaxy formation assumes that galaxies and their central supermassive black holes grow together, that the galaxy forms first or concurrently, and that the black hole grows in step with the surrounding stellar mass. The observations now suggest the opposite. The black holes grow first, faster than their host galaxies, in a sequence that the model does not predict and has not explained. Virgil belongs to a class of objects that JWST has discovered in large numbers that have no clear precedent in the theoretical models and no clear explanation in any current framework. The little red dots. LRDs are compact, now extremely red objects that appeared in enormous numbers approximately 600 million years after the Big Bang, and then effectively disappeared from the observable universe about a billion years later. They may be supermassive black holes in the process of rapid growth, shrouded in dust. They may be something else entirely. Exotic physics, matter-antimatter annihilation, processes that have no name in current astrophysics because no current theory predicted them. George Reiki put it plainly: if little red dots formed in abundance in the early universe, what did they become? Nothing can leave our universe, so their descendants must exist somewhere today. The descendants of the little red dots are among us, hidden in plain sight, and we don't know what they are. Let's now consider what all of these findings collectively say about the model that Hubble helped to build and that JWST is now systematically stressing. The Lambda CDM model is the most precisely tested framework in the history of cosmology. It describes the expansion history of the universe, the distribution of matter on large scales, the properties of the cosmic microwave background, and the formation of structures from galaxies to superclusters with a consistency that has been verified across an enormous range of observations and scales. It is not a fragile theory. It has survived decades of increasingly precise tests. What it is failing to predict is the specific, observationally confirmed properties of galaxies in the first billion years. The galaxies are too bright, they are too massive, they are too chemically enriched. Their central black holes are too large. Their surrounding regions of ionized gas are too extensive. Each individual anomaly examined in isolation might be explained by adjusting specific astrophysical parameters: the efficiency of star formation, the feedback from supernovae, the initial mass function of the first stars. But the combination of all these anomalies, pointing consistently in the same direction — the early universe was more advanced, more evolved, more structured, earlier than the model allows — suggests something more fundamental. Nashwan Sabti, co-author of a 2024 Physical Review Letters paper, testing the Lambda CDM model against the JWST early galaxy data, stated it as a constraint. You cannot change cosmology enough to explain this abundance problem, given that Hubble's observations would also be affected. The problem is not that a simple parameter adjustment is needed. The problem is that no adjustment within the Lambda CDM framework can simultaneously fit both the Hubble observations, which the model successfully described, and the JWST observations, which it cannot. Some cosmologists have proposed modifications to the standard model. Perhaps dark energy is not a cosmological constant, but a dynamic field that was stronger in the early universe, driving faster structure formation. Perhaps dark matter has properties beyond the cold, collisionless particles of the standard model. Perhaps it was warmer, or self-interacting, or had early universe interactions that seeded structure differently. And perhaps the initial conditions from inflation were different from what the standard inflationary models predict. Perhaps the primordial density fluctuations were larger or differently distributed. All of these modifications remain speculative and contested. None has achieved the status of a confirmed alternative. What is confirmed is the anomaly itself. The early universe, as seen by JWST from the edge of the observable cosmos, looks nothing like the extrapolation of the model that Hubble observations built and validated over 30 years. The observable universe extends approximately 46.5 billion light-years in every direction from Earth. Not 13.8 billion, though the universe is only 13.8 billion years old. The number is larger because the universe has been expanding during the entire time the light was traveling. The most distant galaxies JWST has confirmed, at redshift 14 and beyond, existing only 280 to 300 million years after the Big Bang, are at the edge of what any conceivable instrument can detect. Beyond them lies the era of the first stars, and before the first stars, the Dark Ages, the period between the release of the CMB and the formation of the first luminous objects, and before that, the plasma of the early universe itself. The light that JWST is collecting from these objects left them 13.5 billion years ago. It has been traveling across a universe that was expanding the whole time, stretched from visible or ultraviolet wavelengths to the mid-infrared that MIRI detects, and when it arrives, it carries information about a universe that was doing things the model said it shouldn't be doing, at a time when it shouldn't have been able to do them. The growing chasm between theory and observation is not a crisis in the dramatic sense that the textbooks will all be wrong tomorrow. It is a crisis in the productive scientific sense. The data is outrunning the theory, the observations are revealing something the models did not predict, and the process of understanding what that something is will produce the next generation of cosmological knowledge. What Hubble saw at the edge of the observable universe was the confirmation of a model. What JWST is seeing at the same edge is the beginning of a challenge to that model, a challenge whose resolution may require understanding physics of the first moments after the Big Bang that no current theory has captured correctly. At the grain of sand patch of sky that Hubble stared at in 1995 contained 3,000 galaxies, all of them fitting the expected picture of cosmic history. When JWST looked at the same patch of sky and beyond it, with instruments Hubble's builders could not have imagined, it found galaxies that exist when they shouldn't, brighter than they have any right to be, more chemically complex than the timeline permits, with black holes larger than the galaxies that supposedly grew them. It defies logic in the specific scientific sense. It defies the logic of the model that 30 years of observation had established as correct. And the most honest statement the cosmological community can make about what it means is the one that researchers like Kevin Heinlein and Jacob Shen and George Ricci have been making in different ways. Since JWST first turned its mirrors to the early universe, we really shouldn't have found what we found, but we found it. And whatever it means the universe is stranger and less understood than the picture we built from Hubble suggested. The edge of the observable universe is telling us something about the beginning of everything. We are still learning to read what it says. Let me go deeper into the specific physics behind each anomaly, because the overview compresses the technical details that make each one genuinely disturbing rather than merely surprising. The nitrogen enrichment problem in MOM-Z14 deserves full development because it is perhaps the most precisely diagnostic of the anomalies, the one that most directly conflicts with the physics of stellar evolution on a well-defined timescale. Nitrogen in the universe is produced primarily in asymptotic giant branch stars, intermediate mass stars ranging from roughly 1 to 8 solar masses that, in the late stages of their evolution, dredge up carbon and nitrogen from their nuclear burning regions into their surface layers and then expel these elements into the interstellar medium. The key property of these stars, for the purposes of the cosmological timeline, is their lifetime. Intermediate mass stars live for hundreds of millions to several billion years before reaching the asymptotic giant branch stage. The least massive stars that produce significant nitrogen live for approximately 1 to 2 billion years. A galaxy at 280 million years after the Big Bang cannot contain stars that have been living for 1 to 2 billion years. Yes, because the universe itself is only 280 million years old at that epoch. Even assuming the very first stars formed within tens of millions of years after the Big Bang, a generous assumption, since the physics of star formation in primordial gas is poorly understood, there simply has not been enough time for the stellar populations that produce nitrogen to have completed their evolution. And yet, MOM-Z14 shows nitrogen enrichment. The team's proposed explanations are themselves extraordinary. One suggestion is that very massive stars of hundreds of solar masses, more massive than any currently observed in the nearby universe, might produce nitrogen more rapidly through different nucleosynthesis pathways than the intermediate mass stars that dominate nitrogen production today. This requires invoking a stellar population that is hypothetical, that has never been directly observed, and whose properties are calculated from theory rather than measurement. It requires these hypothetical supermassive stars to have been more common in the early universe than any current model predicts. Another suggestion, even more radical, is that MOM-Z14 shows evidence of population 3 stars, the hypothetical first generation of stars that formed from pristine primordial gas. Population 3 stars are thought to have been extremely massive, extremely short-lived, and extremely efficient at producing and dispersing heavy elements. They have been theorized for decades, but have never been directly observed because they lived and died before any current telescope could see them. Yet JWST may be the first instrument capable of detecting their chemical signatures in the most distant galaxies. If the nitrogen in MOM-Z14 is population 3 nucleosynthesis, it is the first chemical evidence of the most theorized and least observed stellar population in the history of the universe. Stars that formed in the first tens of millions of years and left the heavy element fingerprints that all subsequent generations of stars and planets in chemistry inherited. The discovery of their chemical trace in the most distant galaxy ever confirmed would be one of the most significant findings in the history of stellar astrophysics. The JADES team noted this possibility without claiming it as confirmed. We can take a page from archaeology and look at these ancient stars in our own galaxy like fossils from the early universe. Except in astronomy, we are lucky enough to have Webb seeing so far that we also have direct information about galaxies during that time. It turns out we are seeing some of the same features, like this unusual nitrogen enrichment, some of the same features. The ancient stars in our own galaxy, the metal-poor population 2 stars that form from the gas enriched by the first population 3 generation, show nitrogen abundance patterns that match what JWST is now observing in MOM-Z14, 280 million years after the Big Bang and 13.5 billion light-years away. This connection between the deep past of our own galaxy and the most distant observable objects in the universe is a direct chain of nucleosynthesis stretching across the entire observable cosmos. And of the clearing of the primordial fog around JADES-GS-Z13-1 is a different category of anomaly, one that concerns not the internal properties of a galaxy, but the large-scale environment it created around itself. At 330 million years after the Big Bang, the universe should have been largely filled with neutral hydrogen, the epoch of ionization, when ultraviolet radiation from the first galaxies and quasars gradually ionized the neutral hydrogen, clearing the fog and making the universe transparent to UV light, is thought to have been essentially complete by approximately 1 billion years after the Big Bang. But the process was supposed to have been gradual, starting at the locations of the first bright sources and expanding outward over hundreds of millions of years like bubbles in a sea of neutral gas. On a single galaxy at 330 million years should not have been able to clear enough hydrogen around itself to allow Lyman alpha radiation to escape. The ionized bubble a single galaxy creates is limited by its luminosity and the density of the surrounding gas. At this epoch, the surrounding gas is dense, and the galaxy's luminosity, however bright it appears, should be insufficient to create an ionized path through which Lyman alpha radiation could travel to reach us 13.4 billion years later. And yet it did. Kevin Heinlein's statement, "We could think of the early universe as shrouded with a thick fog that would make it exceedingly difficult to find even powerful lighthouses peeking through. Yet here we see the beam of light from this galaxy piercing the veil, captures the phenomenology precisely. The beam pierced the veil. Yeah, that shouldn't have happened. The physics says the veil was too thick. The possible explanations include the galaxy is more luminous than it appears, with additional energy sources not currently accounted for. The galaxy is part of a larger structure, a proto-cluster of many early galaxies, whose combined ionizing radiation has cleared a larger bubble than any single galaxy could create, or the density of the surrounding neutral hydrogen is lower than models predict because something about the early universe's structure formation history is different from what lambda CDM describes. Each of these explanations implies a different modification to the standard picture, and the data cannot yet distinguish between them. The MARY Deep Imaging Survey. On Webb's longest observation of an extragalactic field in a single filter, nearly 100 hours of accumulated exposure time on the Hubble Ultra Deep Field region, produced results published in 2025 that added another dimension to the anomalies. The survey revealed more than 2,500 sources in the tiny patch of sky, including hundreds of extremely red galaxies that are likely massive, dust-obscured systems or evolved galaxies with mature stars that formed very early in the universe's history. The prevalence of these dust-obscured, evolved objects at high redshift is itself unexpected. Models predicted that the earliest galaxies would have had insufficient time to build up significant dust, since dust requires heavy elements, which require multiple generations of stars. The MIRI survey found them in numbers, suggesting that the early universe was dustier and more chemically evolved than any model anticipated. The little red dots deserve more extended examination because their mystery is particularly acute. These objects, compact, extremely red sources first identified in JWST survey data in 2023, appeared in large numbers approximately 600 million years after the Big Bang and then essentially vanished from the observable universe about 1.5 billion years later. They are not rare anomalies. They are a population. Hundreds of them have been identified. Their numbers peak and then decline, and the peak coincides with the era when the models predict the universe was in the midst of active galaxy and black hole formation. The current best hypothesis, supported by the Virgil observation and similar objects, is that many or most little red dots are supermassive black holes in the process of rapid growth, wrapped in thick cocoons of gas and dust that absorb their ultraviolet and optical emission and re-radiate it in the infrared. Seen through instruments that detect only shorter wavelengths, they look like ordinary star-forming galaxies. Seen through MIRI, they reveal their true nature as some of the most energetically extreme objects in the early universe. The disappearance of the little red dots after approximately 1.5 billion years is explained, in this model, by the clearing of the surrounding gas and dust as the black holes grow and begin producing powerful winds and jets that expel the material. At some point, the obscuring cocoon is blown away, the black hole becomes visible as a conventional quasar, and the little red dot phase ends. Yes, the descendants of the little red dots should be the quasars, the spectacularly luminous, actively accreting black holes of the somewhat later universe, and eventually the quiescent supermassive black holes at the centers of present-day galaxies, including our own Milky Way. This narrative is internally coherent and is the working hypothesis, but it requires black holes that grew to supermassive scales in extraordinarily short times, faster than any current model of black hole accretion physics permits. The most massive of the little red dots appear to harbor black holes of billions of solar masses, forming in the first few 100 million years after the Big Bang. The standard model of black hole growth through gas accretion, yet limited by the Eddington luminosity, the maximum luminosity at which radiation pressure can be balanced by gravity, beyond which the accreting material is blown away, cannot grow a black hole to billions of solar masses in a few 100 million years, starting from the stellar mass seeds that first-generation stars produce. This is not a minor discrepancy. The Eddington limit is a well-established consequence of radiation physics. It cannot simply be scaled away. Either the little red dot black holes started from much more massive seeds than stellar mass black holes, seeds produced by the direct collapse of massive gas clouds in the early universe, a process that has been theorized but never confirmed, or they exceeded the Eddington limit, which requires invoking super-Eddington accretion, on a regime that is physically possible but poorly understood, or the standard mass estimates are wrong in a systematic way, a possibility being actively investigated by researchers who note that the dual nature of objects like Virgil complicates mass estimates. George Reeke's statement, JWST, has shown that our ideas about how supermassive black holes formed were pretty much completely wrong, is not rhetoric. It is an accurate description of where the most technically precise observations of the early universe currently stand relative to the theoretical framework that Hubble observations helped establish and that cosmologists have been refining for 3 decades. The universe at its beginning is doing things the theory does not predict. This is not the end of the standard model. The lambda CDM framework has been too successful in too many domains to be simply discarded. The cosmic microwave background power spectrum, the large-scale distribution of galaxies in the nearby universe, the relative abundances of light elements produced in Big Bang nucleosynthesis. These are precise, quantitative confirmations of the model that JWST cannot erase. The challenge is in the specific regime of early galaxy formation in the first billion years, and the nature of the challenge is informing the field precisely which aspects of the model need modification or replacement. But the phrase growing chasm between theory and observation, spoken by a postdoctoral researcher at M1T about the most distant galaxy ever confirmed, captures something that goes beyond a parameter adjustment problem. Thus, it captures the discovery that the universe at its earliest observable moments is more complex, more evolved, more active, and more structured than the 30-year consensus said it should be. The edge of the observable universe is showing us something new. We don't know what it means yet. We know that the models that told us what to expect were wrong, and we know that the instrument that is revealing the wrong answers was made possible in a direct lineage of scientific inheritance by the small telescope that stared at a grain of sand in the sky in April 1995 and discovered that the universe was larger, older, and more populated than human imagination had previously grasped. The James Webb Space Telescope sits at the L2 point, 1.5 million kilometers from Earth, its mirrors cooled to 40 Kelvin, looking outward at light that left its source 13.5 billion years ago. Every photon it collects from the most distant galaxies carries information about conditions in the universe at a time before the Earth, before the Sun, before the Milky Way's disk had fully assembled. Each photon has been stretched from ultraviolet to mid-infrared by 13.8 billion years of cosmic expansion. Each one arrives at instruments designed specifically to receive it and translates the ancient light of the earliest stars into numbers that human minds process, into pictures of galaxies that should not exist the way they exist. The pictures are beautiful. The numbers are clear. The models are confused. And at the edge of everything, 280 million years after time began, something was burning brighter than it had any right to. We found it. We cannot yet explain it. But we found it. And finding it, the act of looking, the act of receiving that ancient light and asking what it means, is itself one of the most extraordinary things that intelligence has ever done in this universe. The chasm is growing. The understanding will follow. It always has. One final anomaly deserves specific attention because it connects the discoveries at the edge of the observable universe to a deeper crisis in the foundations of cosmology that was already present before JWST launched, and that JWST has made significantly more acute. The Hubble tension. The Hubble constant, the rate at which the universe is currently expanding, measured in kilometers per second per megaparsec, has two independent ways of being measured. The first is from the cosmic microwave background. The detailed pattern of the CMB, as measured by the Planck satellite, predicts a Hubble constant of approximately 67.4 kilometers per second per megaparsec when the lambda CDM model is used to extrapolate from the early universe to today. The second is from direct measurements of distance and recession velocity in the nearby universe, using Cepheid variable stars and Type 1a supernovae as standard candles. This method gives approximately 73 kilometers per second per megaparsec. The difference between these two numbers, approximately 8%, is larger than the combined measurement uncertainties of both methods, and it has persisted through decades of increasingly precise measurements by multiple independent teams. Every effort to identify a systematic error that might explain the discrepancy has failed. The JWST, which was expected to resolve the tension by providing more precise measurements of Cepheid distances, has instead confirmed it. The nearby universe is expanding faster than the early universe predicts it should be. A 2025 analysis combining JWST Cepheid measurements with the most precise Type 1a supernova calibrations confirmed the local Hubble constant at approximately 72 to 73 kilometers per second per megaparsec, with error bars that remain inconsistent with the CMB-derived value. The tension is real. It has not been explained. If the tension is not a systematic error, and decades of effort to find the error have not found it, then either the lambda CDM model is wrong, or there is new physics between the early universe and the present day that the model does not contain. The most widely discussed possibility is an early dark energy component, a form of dark energy that was present in the early universe and briefly altered the expansion rate before effectively disappearing. Such a component could reconcile the early and late measurements without violating the well-tested predictions of the model for the large-scale structure of the universe. But early dark energy is not a confirmed component of the universe. It is a theoretical patch proposed specifically to resolve the Hubble tension without independent motivation from any other observation. And the JWST anomalies, the too bright, too massive, too enriched early galaxies, are not naturally explained by early dark energy. they appear to require modifications to structure formation physics that are separate from the expansion history modification. Two independent tensions, two sets of JWST observations pointing toward different aspects of the standard model being incomplete, combined with the little red dot mystery and the primordial fog clearing anomaly and the nitrogen enrichment in MOM-Z14, the overall picture is of a cosmological model under stress from multiple directions simultaneously. This does not mean the model is wrong in its entirety. The CMB predictions of lambda CDM remain among the most precise agreements between theory and observation in all of science. The model's successes are real and numerous, but the specific predictions of the model for the first billion years of cosmic history, predictions that were never directly testable before JWST launched, are not matching what the most powerful telescope ever built is finding. The universe at the edge of the observable cosmos is telling us that the beginning was different from what we understood. Brighter, more complex, more structured, more energetically extreme, more quickly assembled, less transparent to its own light. The Hubble Deep Field began the tradition of looking at the beginning. JWST is completing the view that Hubble could not, and the view reveals a universe that assembled itself before it was supposed to be able to. That finding, specific, confirmed, published in the highest quality journals, spoken about publicly by researchers at NASA and MIT and Arizona and Yale with the specific vocabulary of genuine scientific surprise, is the most important discovery in cosmology since the discovery of the accelerating expansion of the universe in 1998. Whilst it changes the picture of where we come from and how the universe became what it is, we don't know yet exactly what it means, but we know it means something. Something that the grain of sand held at arm's length in April 1995 first showed us was there, and that the mirrors of James Webb, cold and precise at 1.5 million kilometers from home, are now bringing into focus one photon at a time from 280 million years after the beginning of everything. We receive the light. We are learning to read it. The reading is not finished. The universe is still telling us its story. And we are still, after all this time, at the beginning of hearing it. The Nancy Grace Roman Space Telescope, launching no earlier than May 2027, will extend this tradition further, with a field of view 100 times larger than JWST's. Whilst it will transform the handful of record-breaking early galaxies into a statistical sample of thousands, clarifying whether the anomalies reflect local density enhancements or a global modification of the model. The distinction will be made by data, not by theory. What the Hubble Deep Field began in 1995 was not merely a survey. It was the beginning of a tradition, the deliberate act of pointing the best instrument at nothing, at the dark sky between the known objects, and asking what is actually there. JWST has continued that tradition, and found that the edge contains things that should not be there, brighter and more complex and more evolved than 30 years of theory said they could be. The growing chasm between theory and observation is where the next understanding lives, 280 million years after the Big Bang. A galaxy designated MOM-Z14 is burning with light that left it 13.5 billion years ago and arrived at JWST's mirrors in April 2025, carrying news that the universe was doing things we don't understand at the very beginning of time. We received the news. We are still figuring out what it says. The edge of the observable universe is not the end of the story. It is where the next one begins.